Assalamu alaikum students. So in this video lecture we will talk about propane refrigeration loop. This propane refrigeration loop is a very important loop, especially in natural gas processing. For example, in natural gas processing, sometimes your customers they want your natural gas not in a gas form, but he wants in a liquid form. So for that purpose you need to cool down the natural gas so that it become liquefied. So this is your natural gas which you normally use, and if the customer is asking you, I want the natural gas in the liquid form, then you have to cool down the gas so that this gas become a liquid, and then when the gas become liquid, and then you can sell this gas to the customer which he demands. Okay, so the process starts like a chiller. Chiller is kind of a heat exchanger. So what happened inside this heat exchanger, you have one what you call shell and tube heat exchanger. You have the tube side where the natural gas is entering, and also the you can say this is a shell and tube heat exchanger where you're in the shell side where natural gas is entering and leaving from the cold side. Okay, similarly in the tube side you have this refrigerant, the coolant that you are using to cool this natural gas is circulating. So the way the coolant is working basically is like you have the coolant which is in the form of a liquid. When it enters through this tube side of the heat exchanger, so it will exchange heat with this natural gas. When doing exchange of heat, this heat will be transferred from this to this heat exchanger, and in doing this one, this coolant is converted into vapors. So when it's converted into vapors, it will go up. Now this coolant is in the vapor form, so now you can use a compressor to compress it. While you are compressing it, you are increasing the pressure of the refrigerant. This refrigerant then it goes to the condenser where it condense down, or you can say the cooler or condenser. It is an air based cooler, okay, where it condenses down. When it's condensed, it converted into liquid. When it converted into liquid, you can store them into a surge tank, from where again it will go as a liquid and again attached to the heat exchanger. So this process will continues like this. Your refrigerant is liquid, it converted into vapor, compress, condense, store, and then again start the process. This process where the refrigerant is in a liquid form, it's converted into vapor and condense, and then it goes again into a loop is known as a propane refrigeration loop. So in this case, the refrigerant that we are using is nothing but propane. Okay, so propane is used as a refrigerant in this process. So we need to do a simulation of this whole loop, how this loop will work, where you have a liquid, then it converted into vapors, then it condensed down, then it's stored in the surge tank, and then start again this loop. Okay, so we will need to simulate this loop. So this loop is known as propane refrigeration loop. Okay, so to start with, let's talk about first what this refrigeration system is all about. And that, as I explained to you before, refrigeration systems are commonly found in natural gas processing industry and in processes related to the petroleum refining, petrochemical and chemical industry. So these kind of refrigeration is not only happening in natural gas industry, but also happening in petroleum refining, petrochemical industry, and also in chemical industry. Okay, so refrigeration is used to cool gas to meet hydrocarbon dew point specification and to produce a marketable liquid. As I told you before, if the customer is looking for they want the liquid natural gas liquid, so what they ask you to please cool down this, they convert this natural gas into, which is in a gas form, into a liquid form, which is normally known as natural gas liquid as well. So in that case, what you need to do, you need to cool down this natural gas, and the way you can cool down is using a process called refrigeration. And inside refrigeration, what you use propane as a component which is used to cool down your natural gas. Okay, this is one way. And second is like you need to convert this natural gas into into a cool gas, because you want to meet the hydrocarbons dew point specification. Now you know that dew point is a point where you have only small amount of gas, but the rest of the component will be converted into liquid. Okay, in this module we will construct, run, and analyze them and manipulate a propane refrigeration loops simulation. You will convert the complete simulation to a template, making it available for to connect to the simulation. So in this module we need to construct this simulation process, and we need to analyze also. Okay, how we can analyze that if we change something, what is the effect on the other component. So this is what we are doing here. In doing so, we will do some learning objectives regarding the simulation. This one is how we can add and connect operation to a build a flow sheet, which we already do before. A lot of times, all the time when we start with simulation, we will add something, we will do some operation. Second is understand how the simulation of vapor compression loop will work. This is the most important part, how the vapor compression loop will work. The vapor is converted into how the vapor is converted compressed, and then again it is condensed, and then again the process starts. So this is called vapor compression loop. This is the main component what we are studying in this particular exercise. So, and also we need to understand forward backward information propagation in the HYSYS, how we can give some information forward, and some information will be they will be available when the loop is complete. Okay, then again we use inside the HYSYS, we know that we have one of the facility in the inside the HYSYS is the Excel or spreadsheet facility. Okay, we need to use the spreadsheet inside inside Aspen HYSYS to calculate the COP. COP is nothing but coefficient of performance of the loop, how the loop is performed well. Okay, so we need to calculate this one using coefficient of performance. So the example, so in this particular example we have a refrigeration cycle which utilizes propane. So propane is the refrigerant that we are using as a working fluid is used in the liquefaction of natural gas. So we use propane for the liquefaction of natural gas. Propane is fed to evaporator. In this case we are using heater. Okay, heater is a kind of evaporator which is basically used here. And the pressure drop in the heater is 5 kilopascal. Okay, and also some of the other information of the heater is that it has the duty which is 1.5 e raised to power 6 kilojoule per hour. This is the heat that is absorbed by the heater. Okay, and this is the duty of the evaporator or duty of the heater. That information we already have. We have two information for the heater, one is pressure drop and second is the duty. So this duty is used from the natural gas and leaves the dew point vapor fraction. So once this is the information for the heater, so once it leaves from the heater, the stream information, the stream become vapor. As I told you before, it is converted into vapor, and so the stream information that is leaving from the evaporator have a vapor fraction of 1 and temperature is minus 15 degrees Celsius. So this is the information, these are the two information that we have for the stream that is leaving the evaporator. Okay, leaving the evaporator. So the output of the evaporator is then compressed adiabatically with efficiency of 75%. So we need, for compression we need compressor. So after this one, after evaporator or heater, we use compressor because everything is converted into vapor. So now we can use a compressor. The only information for the compressor is its efficiency, which is 75%. Okay, after the compression, then we need to condense it. For condensing we need to use cooler. So we need to cool down those compression vapors. Okay, to reject heat. So how we can cool down? We can use cooler. So after compression we need to use cooler. Inside a condenser or cooler there are pressure drops. The only information that we have for the cooler is this pressure drop, and when it is leaving, the leaving stream from the condenser or the cooler have the temperature 45 degrees Celsius. This is the information we have. It is a saturated liquid, so the information of the stream phase is saturated liquid. Okay, so it will be liquid in this stage. And then liquid means you need to put the information 0 for the stream phase information, and the temperature is 45 degrees Celsius. What you need to calculate doing all of this process is you need to calculate finally the propane passes through a valve, so we need to install a valve after this stream. Okay, we don't need any we don't have any information for the valve, just we need to connect the valve back to the evaporator or the heater. Okay, so once you attach this one to the evaporator or heater, the loop will complete. Once the loop will complete, the simulation will converge. Okay, in doing all this process, what you need to calculate is what is the pressure of the evaporator, that is fed in kilopascal. What is the flow rate of the propane in kilomole per hour? What is the valve pressure drop in kilopascals? What is the temperature of the valve outlet in degrees Celsius? What is the compressor duty in horsepower? What is the condenser duty in kilojoule per hour? This is the information that you need to calculate. After finishing all this, we need to calculate the coefficient of performance or coefficient or COP for the cycle. Okay, so how we can do this? We can use Aspen HYSYS Aspen HYSYS spreadsheet template that we have inside this tool template. Okay, so that will be shown, that will be done after this simulation. Okay, so the coefficient of performance of the cycle is basically measured how much evaporation you have in the evaporator and how much heat is generated, okay, by the heater. We'll talk about this one after so we need to after finishing the simulation. Okay, so let's start with the simulation. But we need to open the simulation and we need to select. Let's go to the Aspen HYSYS. So we need to select the first thing we need to do whenever we are in the simulation environment is to select the component. So the component that we are selecting, because we have only propane that is looping around us in this whole unit, which is this one. So in this whole process, what is looping around is just propane. Okay, so propane is used as a refrigerant. So the only component that we have here, we are not going to talk about the natural gas. Obviously natural gas we need to cool it down, but here the goal is to how to create this loop. Okay, the goal is not to use natural gas. So the only goal in this particular exercise is how we can use propane loop. Okay, that is the only thing. That is the reason why we only have propane as a main component. So propane will be added. This is the only component we have in the component list. The second thing we need to do is we need to go to the fruit package and we need to select a fruit package. The fruit package that we have in this case is Ping Robinson equation of state. So these are the two information that we need to provide. Once we finish with these two information, we need to go on simulation environment. Okay, so in the simulation environment, the first thing we do whenever we are in a simulation environment is to select your material stream. So you select your material stream, you open the material stream, and if you go to your lecture notes, there are two things that we need to provide after we providing all of these. After we are selecting the material stream, what we need to do, we need to go inside of the material stream. We go to the composition, only the composition, and we can put, because we only have propane in this case, so we can put one for propane composition and then click OK and close this one. Okay, so this is the only information that we have so far, because once we complete the loop, then the simulation will be completed. So the second thing what we have is the heater, or you can say evaporator. So we need to select the heater. We can put it here. We double tap and open the heater. We provide the information. We have the inlet information, which is 1. We don't have we can provide the name of the energy stream, so we can, in this case we can give Q1, and for the outlet we can put 2. Okay, once we provide this information, what they're asking is how much is the pressure drop. So luckily we have the information for the pressure drop, which we have two information for this evaporator. One is the pressure drop and second is the duty. So we need to provide the pressure drop in parameters. That will be 5 kilopascal. So make sure you have this proper unit. So we have the pressure drop 5 kilopascal, and we have um the duty, that will be 1.5 e raised to power 6 kilojoule per hour. Okay, so that will be 1.5 e raised to power 6 kilojoule per hour. Make sure you use the proper units. Okay, kilojoule per hour. Once you provide this information, you close it. Obviously it is not solve, because it will solve only when the loop will complete. Okay, so the idea is first you complete the loop, then this will be solved. Okay, and after this evaporator, what we need to do is we need to go to the outlet stream of the evaporator, which is this stream. We open this one, and we know that after the evaporation it will be in vapor phase, so we can put this information 1 for the vapor. Sorry, this will be 1 because everything is converted into vapor. And the second information we have the temperature, which is minus 15 degrees Celsius for the outlet stream. So once you provide this information, you close down this loop. Okay, now after this you need to provide because now everything is converted into vapor, so you can compress it. So you need to use a compressor. So once you click on the compressor, you put it here. You open up the compressor, and you can give the outlet of the evaporator will be the inlet to the compressor. This will be called W1 as energy stream. Okay, and this will be third. So once you provide this information, now what they're asking is the only information that you have for the compressor is this adiabatic efficiency. You go to the parameter and you can provide the adiabatic efficiency. If it is something else, you need to put the 75 here. Okay, the only information we have for the compressor is 75% adiabatic efficiency. Close this one. Now it looks this side. So what you need to do here is you can select this compressor because compressor is showing this side, but we need to show this one in this side. So we need to go to the flow sheet, and we need to see here you have the option for rotate, flip horizontally, flip vertically. So for what we are looking for is to flip it horizontally, so we can click on flip horizontal, so it will looks like this. Okay, similarly you can also flip this stream, which is flip horizontal. Okay, so now it looks like this. Okay, after providing this information, you can go to, you can say we have now we have to use cooler. Okay, so you can click on the cooler, which is shown here. Cooler or condenser, same thing. You double click and open this one. The inlet to this stream will be the third stream. You can call this one Q2, and the outlet will be called fourth stream. Now they are looking for a pressure drop. So what information we have for the pressure drop? We have the information 30 kilopascal pressure drop in the cooler. So we can go to the parameter and put the pressure drop 30 kilopascal. This is the only information we have. We don't have the duty, we have only the pressure drop for the condenser. Okay, you provide this information. Now similarly this one also showing this side, so you click on the flip horizontal part, it will show like this. Okay, after this one we need to install a valve. So click on the control valve, you put it here, double tap and open this one. The inlet to this one is 4, and the outlet, let's first check if we miss anything. Yeah, we miss something. We need to provide the vapor phase fraction for the outlet stream, fourth stream, and we need to provide the temperature. This will be after the This will be at the fourth stage, which will be shown. Uh, yeah, this will be the stream, the fourth stream. So for the fourth, if double click and open the fourth stream, you need to provide two information. One is the temperature, and other is the pressure, other is the vapor phase fraction. So you click here first. You need to give this vapor phase, that will be 0. So because this vapor is converted into liquid after the cooler, so it will be 0. And the temperature of this liquid will be 45 degrees Celsius. Okay, once you provide this one, you close this one, you open the valve again. Here the inlet will be 4, the outlet will be 1. So once you click on the outlet, the loop completes. Once the loop is complete, it will solve, and the simulation looks like this. Okay, so this is how you can solve propane refrigeration loop. So you have some information, not all the information, but once the loop complete, it will solve and the simulation will be converge. So what they're asking us to do is we need to find out few informations. If you go down, what we need to calculate is what is the pressure of the evaporator that is fed, what is the inlet pressure of the evaporator. Okay, that will be this one. So you can see here the pressure for the inlet. You can show this as the table if you want to. I just want to zoom out a little bit. So the only thing you need for this one is the pressure, so you don't need temperature. And you need a flow rate. I think you need a flow rate as well. Yes, flow rate also. So you can leave it like this and close it. So for feed to the evaporator or the heater, you need pressure and the flow rate. What else they ask? They ask the valve pressure drop. So for the valve pressure drop, you click on the valve and you need to show table. So you can see here the pressure drop is not shown. You need to find out the pressure drop. So you go to the table, remove those parameters. You need to add the pressure drop, and this one you add the pressure drop, and it will be shown here. By default it is 183 psi, but it will be this pressure drop in kilopascal will be same as it is shown here, which is 1243.34. If you want to cross check this one, you double click and open this valve, you go to parameter and just scroll it on the top. You can see the pressure is 1243 kilopascal. Okay, you can change this one also from the unit set, but I'm not doing this one, just want to leave it like this. And what else you need? You need the outlet, you need the temperature of the valve outlet stream, which is the leaving this one. So the temperature will be shown here, this one. So again, this is the inlet, so you can add the temperature here. This will be same, which is leaving the valve and entering to the heater. So let's search for the temperature, add the temperature as well. Okay, so you have all the information here. You have this information. What else they required? They required the compressor duty in horsepower and compressor duty in kilojoule per hour. This is related to a compressor, which is this one. Okay, you can put this information in, like if you click here and show table, you will get the heat duty. Okay, now obviously they are looking for both information, kilojoule per hour and horse per hour. So what you need to do, you need to change the units first and then you can add this information. So let me add this information like this. So here, if you look at here in the energy stream, what we need to do, we need to add two things. The first thing is the duty, that will be in BTU per hour. You need to convert this unit in a unit set, that will be in kilojoule per hour. And similarly, you need the duty in horsepower, which also you can get it from first you change it here and then you can get it here. If you want to cross check, you can see here, if you go inside this duty, you can see here the duty in kilojoule per hour is 6.7878 e to the power 5 kilojoule per hour, and in horsepower it is not shown here, but you can find this information uh, from here, which is shown the power is 252.8. You can again go back. Let me go back to this one again. Click on the power. You click on this power, add this power in the table and click done. So that will be shown 252.2 in hot, and this condenser kilojoule per hour here, by default we have the duty in BTU per hour. So if you want to change this one to kilojoule per hour, you need to go to the unit side and change the units here. Okay, so this is how you can do propane refrigeration, and you need to find out those unknowns. This is the first part. The second part is you need to find out the coefficient of performance. So the idea is first we understand what is the coefficient of performance in this whole cycle. So it is the measure of the efficiency of the refrigeration cycle is the coefficient of performance. So the measure of efficiency of the refrigeration cycle is basically known as coefficient of performance, or COP. So it is nothing but it is the ratio of the desired output divided by the required input. This is the formula, the desired output divided by the required input. In this particular case, in the vapor compression system, the net power input is equal to the compressor power. Since the expansion valve involves no power input or output, so the formula will be reduced to evaporator duty divided by compressor power. These are the two things we need. We need to see how much is the evaporator duty, how much is the energy required to evaporate, and divided by how much is the compressor power that we have. Okay, so these two things are required. So how we can put these two information? We can use the help of a spreadsheet that is shown in the palette, which is if you look at your palette here, you have the option for a spreadsheet, right? Excel sheet. Just click on the spreadsheet and put it here in the center. Double tap and open. You click on the spreadsheet tab, and here we need to add some information. Just look at follow your lecture notes. You can see here the first thing we need is evaporator duty. You can call this one evaporator duty. Okay. This one we can put it here. So evaporator duty. Second thing we need is compressor power and COP. So here we need to write compressor power and COP. Okay, first type this information. Now here we need to use evaporator duty. This one I think spelling is not correct. Evaporator duty. Okay, so let's put the evaporator duty. That will be the duty of the evaporator. So you need to right click and import variable. The evaporator is Q1, and the one which we are looking for is the heat flow. So you click on this B1, right click and add import variable. The evaporator duty will be in Q1, and that will be a heat flow, and that will be the one which you are looking for. Add this heat flow, so that will be added. The second thing we need to do is compression power. Compressor we call this one W1, and for this one we click here, add variable W1 heat flow, enter, done. Okay, once you provide these two information, then the evaporator is nothing but the COP is nothing but B1 divided by B2. B1 is evaporator duty and B2 is compression power. Okay, these two information, we just write this formula. So like in Excel, you should start the formula y is equal to B1 divided by B2. B1 is nothing but evaporator duty, so this will take the information from the B1, and B2 will take the information from this cell and click on enter. So the compressor or the COP in this case will be 2.101. That will be the answer. Okay, now after this you can see the coefficient of performance is 2.210. Now the challenge for you, and this is your home exercise, is that you need to change the evaporator duty. You remember the evaporator duty, if you look at here, is 1.422 e to the power 6 BTU per hour, not BTU per hour, kilojoule per hour. Okay, BTU per hour, or whatever you can say. Change this one into 3 e to the power 6 kilojoule per hour, and then see what is the effect on this COP. Okay, this will obviously you cannot do it here in the spreadsheet. You need to go inside to the evaporator and then you can change it from there. Okay, don't change it from the spreadsheet, this will not work. You need to change it from the evaporator inside the evaporator. Once you change that one, then obviously when you go back to the Excel sheet, this will change. You can see and you can put the results, what is the effect on changing this one to 3 e to the power 6 kilojoule per hour on the COP. What is the effect of changing the evaporator duty on the COP? Okay, so this is what we have done in this whole exercise. We create a propane refrigeration loop, and we need to find out, after finishing propane refrigeration loop, we need to find out the COP, the coefficient of performance of this whole loop. I hope you understand the whole process, and if you have any questions, please don't hesitate to ask. Thank you very much for listening to me. Take care and bye.